All right, well, thank you. I'm very excited to be taking part as part of this forum this week. I'm here to share some perspectives and case studies from some of the first permitted and incentive-driven CCS projects in the United States. And so the area on this map is the Plains CO2 Reduction Partnership region. The ERC has led the Peace Corps partnership since 2003, and through our member organizations have really focused on enabling commercial CCS throughout this region. And so as you can see, there's several active CO2 capture and storage projects that are already in operation within this region. There's also a handful of other projects that have been announced, both for CO2 capture and CO2 storage. There's an emerging CO2 pipeline network, and there's additional sanctioned CO2 pipeline projects that'll more than double the pipeline length within this region. By 2025, we're anticipating that there will be over 1,500 miles of CO2 pipeline connecting projects throughout this 10-state, 4-Canadian province region. And so we're seeing our first wave of incentive-driven CCS projects in North Dakota, CO2 point sources, including sources from ethanol production and biorefining, coal-fired power generation, gasification, fertilizer production, natural gas power generation, processing, and other industrial processes. But what's also notable is that we're seeing several capture and storage models move forward from these announced projects as well. We're seeing source synced match projects where you may think of a single project developer that's capturing CO2 and storing it in very close proximity to that point source. We're also seeing source aggregation and storage hub projects where you may have a project developer that's aggregating multiple point sources from maybe one or two, or in one case we have a project developer that's capturing or aggregating more than 32 biorefining and fertilizer production sources and bringing them to a large centralized storage hub where the storage location is more optimized both from a technical and non-technical perspective. We're also seeing capture hubs with distributed storage, so think of multiple storage site developers, multiple point sources, and multiple storage locations, but project developers that are working together through joint operating agreements where they may take advantage of each other's permitted storage sites. So maybe if project developer A will not be injecting for several years but may have permitted storage, project developer B may be able to, through a joint operating agreement, access that storage, and they'll share some of their storage capacity. So if a project has wells that go down for maintenance, they would be able to use the other storage operator's CO2 storage site. It builds in resiliency, and it also helps with provide some redundancy to help these projects with some of their financing requirements. And then ultimately, there are some projects also looking at hybrid storage models where maybe a part of the CO2 is going for enhanced oil recovery or some sort of other utilization. And so the first project I want to talk about today is Red Trail Energy, which is a corn-based biorefinery project in west central North Dakota. This biorefinery takes in about 23 million bushels of corn, produces about 64 million gallons of ethanol annually, also about 233,000 tons of co-products, which include distillers grain, corn syrup that gets sold to cattle feed, and corn oil that gets sold for biodiesel processing. So this project, again, is in west central North Dakota. The Broom Creek Formation is a primary CO2 storage target in this part of the country. It's been assessed previously to this project by the ERC and the Plains CO2 Reduction Partnership. The resource potential of that particular formation is about 10 billion tons of CO2 storage that has been assessed. The Red Trail Energy project is looking at capturing and storing about 3 million tons of CO2, or about 180,000 tons of CO2 annually for about 20 years. So using a very, very small percentage of that resource potential in this formation. The Broom Creek Formation is the target formation. It's about 2 kilometers in depth. It's overlain by more than 1 kilometer of low permeability shales, salts, and some low permeability silts as well. So there's a lot of confining layer between the injection horizon and the lowermost sources of drinking water in the area. Just a little bit more on the formation. It's a Aeolian dune depositional environment. So thanks to hard desert sand dunes that are overlapping. And so the thickness varies, and there is some directionality to the formation as well. I'll talk about that in a little bit, but we did, as part of working with Red Trail Energy to develop the storage facility, took into account through some characterization and the deposition of the formation to more optimally place the injection well on this project to avoid some of the directionality of how the plume may develop. In terms of the capture system at Red Trail Energy, so they're capturing CO2 off the biofermentation process of the corn coming in. And so there's a biofermentation process, the distiller's grains, the alcohol, the ethanol, the corn syrup, the corn oil comes off as part of the fermentation process. And that CO2 stream from the biofermentation is a relatively pure source of CO2. It's over 90, close to 99% purity already, so there's not a lot of additional processing that's needed to really concentrate that CO2 stream. So it goes through a scrubber. Red Trail Energy built and installed a new CO2 liquefaction system that compresses, dehydrates, takes the oxygen out, refrigerates, distills, and compresses that CO2, brings it to about a 99.9% purity. The liquefaction stream does produce a food and beverage grade or quality CO2. If we look at the life cycle analysis of the plant, adding CO2 capture from the fermentation process at Red Trail Energy reduces the carbon intensity of this biorefinery by about 40%. If Red Trail opted not to go through the liquefaction process and not to do that extra purification, it would probably reduce it another 10% or so. But by going through liquefaction, it also opens up that CO2 to other markets if they become available in the future. The other CO2, so capture on the fermentation process reduces the carbon intensity of Red Trail Energy's plant by about half. If you wanted we've been working with Red Trail to look at farther reductions. There's also opportunity to add capture to the heat and power cycle around this industrial process. If much lower concentration of CO2 in a 5 to 10% range, so additional energy, a little bit more complicated to capture that CO2. But if that was captured, it reduced the carbon intensity of the plant much closer to net neutral. If we wanted to look at moving into net negative, adding technologies like perhaps integrating direct air capture, also looking at some of the transportation and ag side of the corn coming in could be another means of moving this plant to a net negative process as well. So the liquefaction plant is set up to process about 700 tons of CO2 per day. Cost to build and install the CO2 capture was pretty reasonable at around $20 million US dollars. Developing of the CO2 storage facility was probably about in that range as well. So for this size of plant, with that high concentration, high purity of CO2, about $50 million to develop and implement CO2 storage at this particular site. If we take a look, just in the upper left is a map. As you can see, Red Trail Energy is pretty close to a small town, Richardson, North Dakota. Less than 1,000 people on the map. You can see where the location of the ethanol facility is, and in orange and blue where that new CO2 capture skid is. The green line represents a new CO2 pipeline that moves CO2 from that capture facility down to the lower or the southeast portion of the map, which is that RTE10, which is the injection well. You also see a white dot, which is a monitoring well for the project. In the lower right, you'll see that same map extent. It's an aerial image, and what that purple outline is the modeled and predicted CO2 plume extent at the end of that 20 years of injection and at stabilization. The white outline is the permitted project area, which is a little bit bigger than the plume extent. That's based on some of the regulatory requirements of where this site was permitted. And that green outline is an area of notification where a permitted project has to notify landowners, mineral owners, and pore space owners around a CCS site as part of the permitting. Just a couple of pictures. You can see part of at the facility, the CO2 scrubber unit that is moving CO2 to the capture and compression facility. Here are just some pictures of the capture island foundation being poured. In the lower left, some seismic, vibra-sized trucks. That was part of a 3D seismic acquisition. In the lower right, you see a picture of the core that was collected from an appraisal well. It's a very unconsolidated or low consolidated sandstone, great porosity, great permeability. You also see a picture in the upper right of an injection wellhead and in the kind of central monitoring wellhead as well. If we take a look at the timeline to develop the project, this is the first CCS project in the U.S. to be permitted under a state primacy program, which means the state, rather than the federal government, issues the permit for CO2 injection. Because of this, there were some federal and state research dollars that went toward helping Red Trail Energy qualify and design the CO2 storage facility component to the project. But this is very much a commercial timeline. And if we look at what development looked like, started out collecting a seismic survey to identify placement of a appraisal well, making sure that there's adequate confinement zones that were throughout the storage project area, drilled the appraisal well, and concurrently, Red Trail Energy advanced the CO2 capture and the geologic storage components of the project, ultimately moving through construction of the capture system, permitting of the storage facility, and to the start of injection. I will say for some of the other CO2 storage projects that we're seeing developed, we're seeing more commonly it's sequential. So we're seeing projects moving forward and permitting the CO2 storage portion of the project first, and needing to have that CO2 storage permit in order to get to a final investment decision on the capture facility and on getting the financing for the project. But in this particular scenario, Red Trail Energy was very much pioneers, and they had a strong business case to move forward with these concurrently. So injection commenced just this summer, June 16th, 2022. They're injecting at an average permitted rate of 180,000 tons of CO2 annually. But the project itself and the well is able to inject at a much higher rate, if so desired, almost up to 4,100 tons per day. So the well is overbuilt, and the formation is such that it can handle a lot more CO2 than that's being injected for just this project. And these are just some pictures from that commissioning ceremony and some of the capture system. Outreach, and we talked a little bit about this yesterday, but that outreach was a very important component of this project, not only to get buy-in from that local community, Richardson, which was not too far from the location, but a nuance in the U.S. is that the pore space is owned by the surface owner in North Dakota. So Red Trail actually had to go out and execute lease agreements with the surface owners in order to store CO2. So Red Trail Energy, also the ERC through the Plains CO2 Reduction Partnership, and other projects being developed have engaged in pretty active outreach campaigns around what CCS is, why it matters, how it relates to the community. And that was a very important part for Red Trail Energy to make sure that there's accurate, timely, factual information going out that they can use to help inform those landowners that they had to negotiate pore space agreements for. And ultimately, based on some of the work they've performed on surveys, saw a very high acceptance rate for the project in the local area, upwards of 95%, which was a very positive to see. We also worked with Red Trail Energy and we performed several risk assessments throughout the development of the project. And I just think it's notable to note that the risk profile of the project continued to be reduced as the project was developed. So as we started working through the site design, collecting data, progressing in our design operation, drilled an appraisal well, qualified the location, got to design parameters, started modeling and optimizing location of the well, the injection and the monitoring well. We placed the monitoring well in an area that was in the middle of one of those sand dunes so that we didn't have as much directionality with the plume or uncertainty with the plume. Started refining, getting capture bids, commissioning and contracting the build of the site. That risk profile was decreased. Also, I mentioned this project was one of the first projects to move forward under state primacy, and so there are some external factors that also helped reduce the risk profile. North Dakota attained the UIC Class 6 primacy, or the ability to permit CO2 injection wells as this project was being developed, and so that added more certainty in terms of the process and timeline to permit a project. We also saw some of the incentive programs and markets that Red Trail Energy was selling CO2 in to get incentives for that storage, came out with additional guidance or release protocols that made it a little bit more certain that Red Trail would be able to qualify for the incentive programs around this project. I would just encourage you, if anyone has interest in learning about biorefining, learning about ethanol production, learning about how CCS integrates, Red Trail Energy has an outstanding YouTube video on their website that takes about 10 minutes to step through the ethanol production process and why CO2 is an important part, and it's a really well-made video. So encourage you to take a look at it if interested. So most of the other projects I talked about that we're progressing within the region are outside of the ethanol production, are focused on capture and storage from large coal-fired power generation and natural gas processing units. But the other one that stands out that I think is worth noting is the Great Plains Synfuel Plant. And so this is a lignite coal gasification facility in North Dakota, and it's a chemical processing plant that's producing products through coal gasification. So the Great Plains Synfuel Plant produces pipeline and liquefied natural gas, so it produces synthetic natural gas. It does produce carbon dioxide that's sold for EOR and food and beverage markets, liquid nitrogen, krypton and xenon gases, hydrogen, naphtha, emission control chemicals, and fertilizers like anhydrous ammonia and urea. This is the first project that started capturing CO2 in North Dakota. It's been actually capturing since the year 2000, so a little over 20 years. It uses an amine capture process off the backside of the gasification, and it's captured more than 40 million tons of CO2 per date. But what's interesting is now they are looking at integrating CO2 storage beginning in 2023 to capture and store the remainder of the CO2 that is not sold to markets, and so they're adding additional capture. This project is looking at scaling up from 1 million to about 3 million tons of CO2 captured annually. And what's interesting, this is the first project I'm aware of in the region that's looking at implementing a pattern injection approach in order to optimize storage and a project footprint. So think of instead for a project a little bit bigger than or a storage facility area, a little bit bigger than Red Trail Energy, they're putting a lot more, a whole order of magnitude more CO2 in the ground. And they're doing that by, instead of 1 or 2 large injection wells injecting 1 million or 1.5 million tons a year, they have 6 injection wells. They'll be injecting a couple 100,000 tons a year. So what that does is it allows you to get more CO2, a higher CO2 saturation or a higher storage efficiency in a smaller area with more injection wells at a smaller rate. So I just want to wrap up on one idea. These are the permitted storage facility areas of several projects that have been permitted in a portion of North Dakota. The purple outlines are the storage facility areas. The red outlines are what's called the area review, or the area you have to look at potential leakage pathways because of the pressure elevation from injection. There is a lot of heterogeneity in some of these sites. The footprint and the area review is very influenced by geology, and the pressure is also very temporal in nature. The highest pressure in the formation will likely be at the end of injection, and it will dissipate over time. You see one site where there's multiple outlines. That site is actually taking a stack storage or injecting into multiple horizons. But I want to put this up here on the screen to start thinking about, as we go on the screen, we have about 7 million tons of permitted CO2 storage. If we look at how do we go to 50 million tons or 100 million tons or 1 billion tons of CO2 storage, you can start imagining as you have more sites on this map, you may start running into pressure interference between projects or pressure communication. And so I think this is an emerging topic that we're going to see as we look at how do we go from millions to billions of tons of CO2 storage, and you start putting in projects close to each other. I'll just wrap up with this. Every project developer that I have the privilege of working with is also looking at, once they have a storage site, and understanding once a site's permitted, once it's operational, once it's performing as expected, you've de-risked that storage site because you're operational and you can see it's performing as expected. And so there's also a strong look at what do I do and how do I expand that storage site in order to get more CO2 in or additional sources of CO2 in over time. And so there's ways to do that. You can expand the storage facility area, make it bigger to increase capacity. You can add more wells, like I mentioned, Great Plains Synfuel is doing, in order to get more higher storage efficiency, increase storage capacity. You can add stack storage, like Project Tundra that I mentioned, where you're injecting into multiple horizons. Or you can do things like active reservoir management, or maybe you're producing brine out of the formation to make more space for the CO2. And so I think this is how do you expand storage facilities to accommodate more CO2 once they're operational is another topic that I think we're going to see of growing interest as we look at how do we get to billions of tons of CO2 storage. So with that, I'll thank the members of the Plains CO2 Reduction Partnership. So these are all the prior and current members since 2003, which are allowing me to be here today and has really been a big part of the work we're doing. So with that, thank you all and for the opportunity to present this morning.